Okay, one last rule that I wanted to kind of go over, a relation, is orthogonality. Okay, so we say that, excuse me, A is orthogonal to B vectors if the angle between them will make a 90-degree angle. Okay, so this orthogonal means 90-degree angle is between the two. Okay, so if I were to extend these vectors, even though they're not lined up with each other, we can extend them and again make a right angle. Okay. Okay, so I'm going to move that out of the way. Excuse me. Vector addition. Okay, this is also called the tip-to-tail method. This is a way to add vectors graphically. Okay, so if I have two vectors, let's say A and B, okay, these are my two vectors, and I want to add them together. What I'll do is I'll take the first one, like that. It's a little long, but you get the idea. This is supposed to be the same as that. And add the second one from the tip to its tail, like that. Okay? And so our resultant vector, that's what this R is called, resultant vector, will be from this tail to that tip. There, this is now R, our resultant vector. So again, this was A, B, adding the two, we get our resultant vector here. Okay, let me change my pen color here. Okay, all right, so I have another example here. Okay, again, if I have A, that's just going this way, B, that's going this way, we go from the tip to the tail. Okay, and this would be our resultant vector, or R. Okay. If we have more than two, say we have three vectors, the same idea will apply. You'll put vector A, and then you'll put vector B on its tip here, and then C added to it, and then from the beginning of A to the end of C, that will be our resultant vector. Okay, so again, when I'm saying R, I mean resultant vector. Okay. Okay. Now, if I do the same sort of thing, but now I have a subtraction of two vectors. Okay, so this is the same as saying A minus B equals our resultant vector. Okay. So I always think of it as adding a negative vector, okay, instead of subtracting. And here's why. So if I have A that's this way, okay, and I'm adding a negative B, and say B is originally this way, okay? So this is my negative B, this is B. What this really is going to be this A plus negative B, which just changes the direction. It doesn't change the magnitude, it changes the direction of the vector. Okay, so now this will give me A plus B, so again, tip to tail, something like that. And then my resulting vector is going to be here. Okay. Versus what I would have had if I did it incorrectly, I would say A, or I guess not incorrectly, but this would be A plus B. It would be like so. And see how that changes my resultant vector. Okay, the magnitudes are a little off, my directions are a bit off, but not completely, but you can see that this will change my direction of my resultant vector. Okay, so be careful when you're doing this. Make sure you take that negative into account. Okay, and here we have multiplying and dividing vectors by scalars. Okay, so if I have some vector A, okay, that looks like this, and I want to multiply it by 2, so multiply it by a vector, okay, it would just be taking that magnitude of A, so whatever this little length is, okay, remember that's the magnitude, and multiplying it by 2. Okay, so now this is my new vector. Now if I do the same kind of thing, but now dividing it by 2, I get that my original magnitude was this long, say, and now I have a magnitude divided by 2. Okay, so just pointing this out, it's similar to multiplying by a negative, but of course that is going to be changing its direction. Okay, so if I have a negative A, that is going to be the exact same magnitude, but in the opposite direction. Okay? All right, one thing I wanted to point out on this slide is that we can't really multiply or divide vectors by vectors. We do something sort of similar, but it's not just straight, you know, A times A sort of thing, A bar times A bar. Okay, it's a little bit different than that. Okay, or A divided by A. That's not something we can do. Okay, so let me go ahead and talk about coordinate systems, and then through that we can talk about breaking down vectors. Okay, so we have two coordinate systems that we will probably be using, okay, which is Cartesian coordinates and polar coordinates. I'm not sure if we will get into spherical, but we might, we'll see. Okay, so Cartesian coordinates, and this is just in 2 dimensions. Okay, so we're looking at 2-dimension coordinates here. So Cartesian is the typical XY axes. Polar coordinates are based on the radius and the angle between the point, whatever your point is, that radial vector, and the x-axis. Okay, so again, if we're looking at vectors here, so this is my vector v, I'll say, and this is my vector r. Okay, they're going to be described in a little bit different ways. So this one's going to be based on x and y. This one can be based off of r and theta. Okay, so what we can do to transcribe between the two, or translate between the two, is using the Pythagorean theorem and some other trigonometry information that we know. So remember, the Pythagorean theorem is a squared plus b squared equals c squared. Okay, we should remember that from algebra days. And then we want to remember our trig days of SOHCAHTOA. Okay, remember that SO is going to be sine equals opposite over hypotenuse. COT, or cosine, is equal to adjacent over hypotenuse, and TOA, or tangent, equals opposite over adjacent. Okay, and so using these, we can translate between our Cartesian coordinates and our polar coordinates. Okay, so Cartesian to polar and vice versa. Okay, and how we were able to get here is simply by looking at this graph right here and saying, okay, if I'm looking at this angle here, theta, and I want to find y, I guess, then I can say, okay, opposite, right? Opposite over hypotenuse, which is r, equals sine theta. And if I want to solve for y, I can say y then is equal to r sine theta. Okay? And same thing here. I can say x equals to r cosine theta. Okay? And if I want to know that angle, maybe, I can take this or any of the other ones if I know the other values here. But I can say theta is equal to tan inverse of y over x. Okay, so these are just some general ideas of trig, okay, that we'll be using. Now, when we're looking at vectors, we want to break these down into their components, okay? So if I have a vector A here, see again, we have bolded text instead of the bars, okay? What we can do is we can break this down into our component vectors. So a bar is going to be the same as saying ax bar plus a y bar. Okay, this tells us that they are in the x and the y directions. Okay, another way of saying that is ax, and I'm gonna use these things called unit vectors. Okay, so in the x direction, it's typically I hat plus ay j hat. Now, if I had a third axis here, so if I was in 3 dimensions, I could say my last unit vector would be k hat. Okay, but we don't need to worry about that right now. Okay. All right, so this is, well, give me 1 second. Okay, sorry about that. My computer was dying. So looking at component vectors, we can break it down into our x and y coordinates, and we can also describe them in terms of our trigonometry here. Okay, so let's see. We can say that this side here is the same as ay. Okay, this side here is the same as ax, right? Okay, so if I want to know what our magnitude is here or here, I can say, okay, well, opposite over hypotenuse, I can say sine theta is equal to ay, and these are just looking at the magnitudes. These aren't the vectors, okay? Ay over a, okay? And I can solve for ay, so now ay equals a sine theta, okay? I can do the same thing with ax. I can say cosine theta, because this is adjacent, over hypotenuse. So ax over a, so then we get ax equals a cosine theta. Okay. We can also get the tangent of theta is equal to opposite, which is ay, over adjacent, which is ax. Okay. And in this here, we can solve for theta. So theta would be equal to tan inverse, or arctan, of ay over ax. Okay, so this is the way to break down your vectors into components. Okay, and we'll see why that's important in the next video. For now, I'm going to stop here or pause here, and then we can continue in the next one.